2, 1, normal distribution. So introduction to the bell curve. As you're studying continuous probability distributions, one of the major ones in the beginning, so in data management, most likely around grade 12, or maybe later on, or maybe earlier, you're going to run into this normal distribution. So please remember, continuous probability distributions are density functions, right? Where we have to take areas under the curve between intervals to find out what the probabilities are between particular intervals. Now, the normal distribution is one of the nicest distributions to work on, and there's huge amounts of data on the normal distribution. It's symmetrical, it's unimodal, it has your mean, your mode, your median, they're all the same. Okay, so it has a lot of really nice properties, and there are various items in terms of the overall population that fall in this type of probability distribution. For example, population heights, okay, will typically fall around there. Okay, there's many others in terms of manufacturing, services, okay, and many others. I'm not an expert in which ones they are, but I do like the math behind it, so I want to introduce you to this bell curve. So, I drew this bell right here, as you can see, and I'm going to show you that this normal distribution kind of looks like a bell. Now, I will make the assumption that, you're familiar with the mean, okay? You're familiar with standard deviation, okay? So you see that on the green, okay? So that's for the population. So those are the symbols that I'll be utilizing. And then there's also ones for just the sample. But because we're working with continuous probability distributions, I'm assuming that we're working with the entire data. So it's going to be the green ones that I will work with. Now, another item that I'll assume is that you're familiar with the Z-score. So it is just how many standard deviations away is a particular data point with regards to your data set. So that Z-score is just X minus your mean divided by your standard deviation. Now, if you forgot any of this, okay, I would encourage you, especially kind of standard deviation, take a look, okay, I'll put up a link up above there. So I think it is worth your time, okay, to be able to refresh yourself on it. And then on the Z-score, how to calculate it, okay, I'll put up a link up above there for that. So now, as you see this very fancy bell, okay, that I drew here, so I'm going to slowly, okay, what I'll do is, okay, so obviously it's not a full out bell, okay, that we have in terms of our function or our probability distribution. So I'll remove some of these. I'll remove the handle, all right. I'll remove, I think it's called the clapper, okay, so this thing inside here, okay, so now it's kind of just looking like this. And then what I'll do is, I'll remove so that it's kind of not looking like three-dimensional, but it looks like this. And now once I have that, so this is the function that we're going to be interested in. So I'm going to map it on, so like, right here, okay, kind of like that. Okay, I'll try to center it around there. And as you can see, so that's why we call it a bell curve. And again, so it is unimodal, so it has just one, big hump. It's symmetrical. Now it's going to turn out, okay, for now I'm going to assume that, it's symmetrical around 0, but it will be actually symmetrical around your mean of your entire population data. Okay, so you can assume that the origin is actually the mean, okay? And now, how can we model this, okay, throughout? So you maybe have watched, okay, the video or studied exponential distributions. Okay, so I'll put up a link up above there if you don't remember that. But the exponential probability distribution was a nice introduction because this bell curve, this normal distribution that we have, can be constructed from the exponential. And now I just want to show you how we can come up with this curve, and it will play on what you have learned in your function. So in grade 11 course, okay, on this. So I'm going to take out decimals because I really like working and then illustrating things through decimals, right? So now if I have my function, so let's say this is my function, and it's going to be an exponential, and I'm going to use Euler's number, so the constant e. So if I have this and I try to graph it out, so e, okay, so to the exponent of x, so we know that it looks like that, right? Now, okay, if I now on the other hand, okay, make this decaying exponential, so as x gets bigger it starts to decay. Basically it's just, okay, a mirror image, okay, if you remember transformations, because I'm just multiplying it by negative. So with regards to that, so it looks like that. Okay, so far this would have been just an exponential. Now on the left hand side of the origin, right, so on the negatives, okay, as if that's my domain, which is less than 0 there, you notice that it's blowing up, right? As x gets smaller and smaller, it's blowing up. Now if I actually would square, okay, so if I would square this, okay, instead of having just an x, notice what's going to happen. So what's going to happen is, because you're squaring your x, so that means all your negative values, basically you've now created a symmetrical, right? So this is the symmetry, so it's a symmetrical function. And you can certainly do the test for the symmetry, right? So if you remember odd and even functions, okay, so throughout that, and that is because it's squared. So now the negative, so for example, if you substitute -1, okay, and you have 1, it's going to be exactly the same y value that we have. But this is the actual bell curve. So this is how, okay, they were thinking about the bell curve throughout. And from this bell curve, okay, we can go ahead and start to introduce the standard deviation of the entire population. We can introduce the mean, so that there is actual meaning behind this bell curve. And then we can start calculating probabilities. So we know that the area under the entire curve has to equal to 1, right, for the probability distributions, because that's just by the rules of probability, that all the probabilities sum up to 1. So how did we do that? Okay, and so this, basically this bell curve, is nothing else but just some kind of an exponential. Now, I chose the letter E because it's standardized, okay, within mathematics, statistics, and numerous others, okay, because it's naturally occurring, and it's very, very helpful. It's in terms of the exponential that you use. But it could have been any exponential that we had. So far, okay, what I have for you is that this is kind of looking like this right there, right? So that is, and it is basically around 0. Now, if you think about it and you start thinking about, well, the mean is not always 0, right, for your data set. And of course, it's most of the time it's not 0. Let's say if you're talking about populations, well, population height, well, number one, it's not going to have any negative values, period, right? Okay, so there's nothing in terms of the heights that we have, so those heights are going to be distributed across more on the positive side. So I can change this up. And again, so please remember, if you have, so h, x minus h, so this is a transformation. What did this actually do when we were doing transformations? Well, all it was is it shifted, right? It was a translation in the x. So this would have translated it by h, okay? So this would have got shifted, okay, by h to the right, assuming h is positive here, and it would have been just a shift. Now, what we do, so in statistics, so this normal distribution, okay, to try to kind of come up with it, well, we said that we want the midpoint to basically be our mean. So our h right here is nothing else but the mean. Okay, so that's what we actually started to do. And if you do that, now of course, as you're shifting it across, so if I go back in here into decimals, so if I'm going to be shifting it back and I say f you know, x and whatever this might be. You know, put a slider here, okay? So notice that it just shifts it to the right, right? And this will shift it to the left, okay? So this would have been your mean. So now your bell curve, your normal distribution, is just shifted around your mean. So that's what happens in here in terms of the functions, okay? So that was one thing that we had. Now next, okay, so what we have is, so we've seen that it's basically just shifting it around the mean. Now we do want to be able to kind of normalize this, so this normal distribution or this bell curve. And what we end up doing is, so with regards to this particular, okay, so function that I started off here, right there, okay, so what's going to happen is we're going to, if you remember transformations, you can actually compress or stretch, right? So your parent function, so this would have been our parent function here, okay, if we have a d in here, so and this is going to be d, so this is x minus h, so this is the d. I actually talked about transformations, I use these constants d and h. Okay, so this d is basically the compression or the stretch, okay, within. And now what we do is, okay, so interestingly enough, we're actually going to, okay, so stretch and compress it, okay, with regards to our standard deviations. So this, okay, is actually what's going to happen, okay, within here. And now if you would substitute that, okay, into our function, so it's going to be e, okay, minus, all right, now you can put 1 over the standard deviation, so that would have been 1 over the standard deviation, okay, all over, this is x minus mu, and this is all squared. Or, of course, it's much nicer to just write it as x minus mu, okay, and put the standard deviation below there, okay, and this would have been our new transformed function, and it introduces you into, it's centered around your mean, and it's standardized with regards to that standard deviation. Now, what you might notice, x minus the mean all over standard deviation is actually your z-score. So if you substitute your z-score, okay, if this was your z-score, then really what you get just your standard normal distribution, where you're just around 0 back again if you're doing it with regards to z-scores. Now, for that, all right, so if we had all of this, so great, you know, we're moving our, okay, normal distribution left or right depending on what the mean is, you know, we have that standard deviation in there. And now lastly, we have to be careful to make this thing a true probability distribution. So if we would sum up the area under the curve, it had to equal to 1. And it turns out that we would need, okay, basically a constant multiplier. So this is like your, you know, multiplying, or again, this would have been your entire transformation, okay, of your original function by some a. And it turns out we normalize this by, okay, so this would have been 1 all over standard deviation, okay, over the square root of 2 pi. Now you might say, holy, how could I have possibly known that? Well, you wouldn't. You know, this takes a long time, okay, so statisticians, mathematicians were working on it, okay, and then they were actually doing this to try to get this normal distribution as an overall function. So this is really neat. Now, there is one thing which is missing here, which I didn't introduce right in the beginning because I wanted to start with something very simple so that you can see that it models this bell curve. Okay, so technically our parent function isn't really just this. It's actually e to the negative 1/2. Okay, x squared. All right, but it doesn't change anything that I have just done here. Okay, just to show you how you introduce your mean. Okay, so everything is the same. So if this was your parent function, and then you introduce, you know, first this, okay, then your standard deviation, and then now you introduce this term, Okay, so this a, which is 1 over standard deviation and the square root of 2 pi, then it all works exactly the same. So now that a, again, if you remember transformations, okay, if you multiply that, all it does is it just stretches and compresses in the y, right? So that's what it does. So it stretches in the y, the d stretches and compresses in the x, okay, and then your h, which is really just your mean, where your mean is, okay, will just translate it left to right, okay? Now, if you really want to think back of transformations, I'll put up a link up above there to the original one, but for this purposes, okay, this is probably much different than any introduction to the normal distribution that you have, because I'm doing it through the viewpoint of just functions. Most of the time in statistics, as students take it, okay, they don't want to think about the functions, and then they're just given the equation, and then they say, here it is, and then no one really understands. So I hope that this walkthrough just makes you, think about that. Oh, okay, so this is just an exponential, it's decaying. Okay, we squared it just so that it looks like a bell. And this bell, okay, nicely captures a lot of probability distributions in real life. And we use it. Now, it's purely symmetrical. You can see it. Now, even if you wanted to calculate probabilities, because it's so symmetrical and you know the probability across the entire thing equals to 1, so that means if you take your mean, so to the left of the mean is 50% probability, to the right of the mean is 50% probability, okay? Now, there are other properties, which I'm just going to show you in just a moment, where you can capture quite a lot of the probabilities within standard deviations. And that's the beauty about this, and that's why it's so heavily studied. So in general, okay, so what we have, okay, within here, so maybe let me remove this, okay, I just want to show you. So this is our overall normal distribution, okay? If you look at it as a function, what I would want you to think about is, okay, I know how it looks like a bell, right? All I've done is really just transform, so I'm just shifting things around. So it is being centered around my mean, and it is being normalized, okay, so that the probabilities work out by this factor, okay, and then you have your standard deviation within here. Now, this, okay, inside really is just your z-score. So as you studied your z-scores, if you haven't, okay, you can take a peek at that video I pointed out in the beginning, okay? So that is your normal distribution. And if you are doing it around your z-score, meaning if your mean, so if your mean is equal to 0, and then your standard deviation is just equal to 1, so then this entire thing would have fallen off to really just this. So it would have been e to the negative 1/2. Okay, this would have been x squared, or you can just put it as z, okay, because that's what z would have been, okay, from there. So this is called your standard normal deviation. Standard normal distribution. So that is just assuming that you're around 0, and then your standard deviation is 1. Okay, and now with this, okay, there are numerous tables that you can find to actually work these things out. Now, if I show you this, so if I go back to the original, so let me go back to decimals in here. Okay, so if I have my function in here, so let me do this. So this would have been 1, okay, divided by, so the standard deviation, okay, so that is, now I'm going to normalize this whole thing. So this is the square root, okay, so it's going to be square root of 2 pi, all right, and there you have it. Okay, so now let me shift this away, and that is really what your bell curve, standard bell curve, would look like. Okay, so that's what we have right there. And now from here, you can do, whatever it is that you like. Okay, so if your standard deviation changes, okay, and your mean changes, you can update this as you go. So in any case, okay, it turns out that, for instance, if you're using decimals, you wouldn't necessarily want to type out this entire function, and it's same thing for graphing calculators, Excel. It is so commonly used that it's going to be included in the functions that you have. So if I, scroll down to statistics here, okay, so distributions, normal, notice it says normal distribution. So that's what you have. So if I map this, so, if I have a mean, okay, of basically 0, and I have a standard deviation of 1, so 0 and 1, okay. Oh, and notice that, so this is because if I go back to the original, this was supposed to be 1 over 2, so this is 0.5, okay. So that's what we have there. So notice they align on top of each other. So instead of doing that, okay, and writing out your full equations, so these equations that you have, like you don't want to be writing out this thing you can actually, in decimals, on graphing calculators and so on, okay, just find your normal distribution, and all it asks is what's the mean, what's the standard deviation. Once you have those two, okay, so if these changes, let's say the mean was 3, so notice it's going to shift it by 3, so that should make sense to you, because it's just a translation. And let's say standard deviation was now, I don't know, 2, okay, so notice it flattens it out. All right, so it's just flattened out around, so the bell just kind of looks a little bit different, okay, like that. If you put, this, and let's say, I don't know, it was very small, so let's say 0.2, so notice it just starts to shoot up, okay, right there. That's what we have, okay, with respect to these. So these bell curves, now of course, if I zoom in, they can all look the same, just depends on what scale I'm using. Right, so if I can do that, you can nicely capture it in. There you go, you have your bell. So that normal distribution is super useful. Now, some properties of this normal distribution, okay, that you have. So I'm gonna just map this out. So here it is. Here's your bell curve, right? I mean, I drew it out, so it's not as nice as it is on decimals. Now, what is so neat about this is that you'll notice that we are centered around, so this is, mu. So if I go back in here, let me just copy this down, just so that you can see this. So let me copy it and bring it down, and then map it. So let's say, okay, this is my normal distribution. So all of this that you see in here, so your mean is where it is centered, and now it's completely symmetrical. It turns out, if you wanted to calculate the area under the curve, so if you were going from, so for instance, okay, if you wanted to go from here to here, so within one standard deviation, so all within the population, it turns out that 34%, okay, that is the probability that to the right of your mean, 34% of the data will actually fall. So that's the probability that you're going to be within one standard deviation to the right. Now, because it's symmetrical, it's also 34% to the left, which means that within one standard deviation, so to the left and to the right, you're actually at 68%. So that is a super high probability that you will have. So if you did the area under the curve, you would be able to find that within here. Okay, so within that one standard deviation that you have. So that's pretty neat. All right, and now as you move over, notice because the bell curve so it just starts to go down, the probabilities get smaller. So here, notice from one standard deviation to the second standard deviation, so right here, it's about 13.59 or about 14%. Okay, and the same thing happens right here. Okay, again because of symmetry. So within two standard deviation, so what's the probability that you will fall within 2 standard deviations, okay, around your mean, it's literally 95%. Okay, and within 3 standard deviation, notice you're almost 99.7%. So these, you see this very often because it's not always very easy to calculate the area under the curve, okay, as you maybe have seen in the video I did on the exponential probability, okay, distribution. So because of that, these numbers, they're always the same. So as long as you know what the standard deviation is, it doesn't matter if it's stretched and compressed. All you have to know is, okay, how far are you within these standard deviations? And then you can tell how much of your data, okay, and what is the probability that you're going to fall within that range. That is really useful to have. And these, okay, types, okay, of diagrams where it's broken down, 1 standard deviation, 2 standard deviations, 3 standard deviation. Notice beyond that, probability is tiny, right? These are kind of outliers that you might have there, okay, because it just fades off. And of course, we see that within here, right? So within your distributions. Now, what's neat about, for example, decimals. So if I have decimals within here, so, you know, this says that the mean is 3 and then my standard deviation is 0.2, okay? So if we were doing that, so I just want to show you, okay, what decimals can do with respect to calculating these probabilities. So let's say, you know, so I said we have this as an example. So my standard deviation was 0.2. My mean was equal to 3. So based on this, like, what does this mean? So that means that, for instance, if you wanted to find out what the probability is, okay, that you're going to fall, okay, between, let's say, 1 standard deviation to the right, so that would have been 3.2 around the mean, and then from 3, so that would have been that 1. This tells us that it should be around 34%. But we would have to calculate the area under the curve, right? So this is around 34%, always, okay, always. So again, okay, I'm not going to calculate the standard, the area under the curve in here, but you notice there that it says find cumulative probability, right, in that normal distribution there. So notice I'm going to click that. And now it asks me, okay, and it gives me a number equals to 1 because it has taken the entire, okay, area under the whole curve. But what I want is for here, I want it from 3, okay, to 3.2. And notice 34, okay, 1, 3, 4, 4, and so on. So about 34%, which is exactly, right, if I go back into here, okay, so 34.13, so that was rounded to 2 decimal places. Typically, we just say 34. So that is what you see there on decimals. And now, if you wanted it within 1 full standard deviation, so 0.2 from the mean in both left and right, so this would have been 2.8. Okay, notice 68, okay, percent. So and it shows you that within here. So it highlights it. So I mean, decimals is amazing with regards to this. So, and you can do that for any, and it's always this. So if you change your standard deviation, okay, and your mean, then, you know, the numbers would change. So for instance, if I would say, okay, let the standard deviation be equal to, let's say, I don't know, 3, okay, and let the mean, okay, be equal to 100. So, and now you wanted to find the probabilities again. So now, let's say within 1 standard deviation. So that means you're basically, well, the mean is 100. So 1 standard deviation you're looking for, okay, the probability that it would have been, so left to right, this would have been 97. So this is the probability that you're within there. And it's always going to be 68%, okay, within that. And you don't have to calculate anything, okay, if you know that. So here, you know, let me change this up. So I said what? 100 was the mean, and then this was 3. So here we're going from 97 to 102. Sorry, 103, I believe. Yeah, 103. So that is 68%. Okay, hopefully I did. Yeah, so 97 to 103. Again, you see that. And you can play around and then see, okay, so where are we? Now, of course, this has disappeared because it's at 100, right? So this is somewhere over there. Where's 100 here? And we can zoom in here. So that is the introduction to your bell curve. Okay, I showed you where it comes from in terms of the exponential. It's not a very nice function, but if you, the key point is to understand it. And if you understand transformations, you know, it won't be that difficult to grasp. And of course, the beauty with it is the symmetry that you have. Okay? All right, thanks for watching. We'll see you in a future video. Bye, everybody.